October 2025. Above the silent red plains of Mars, something outran the stars. Perseverance's night sky cameras, normally meant to track constellations and meteor trails, captured a razor-thin flash slicing across the darkness, its speed 60 kilometers per second. Its timing and direction, a perfect match for interstellar visitor 3I Atlas during its historic Mars flyby. Then everything went dark. Within hours, scheduled Mars orbiters, MRO, TGO, and Mars Express, stopped transmitting raw image data. The live feeds froze, the archives went quiet, and before anyone could analyze the footage, the images vanished from public access. Rumors spread like wildfire. Amateur astronomers whispered about multiple fast-moving objects near 3I Atlas and a brief green flash seen in one frame. NASA and ESA said nothing. The world's scientific community was left staring into silence, wondering whether something extraordinary had just crossed our neighboring world. The official explanation? Calibration delays. But behind those words, suspicion grew. If the data were routine, why the blackout? Why now? At the very moment an interstellar object swept past Mars. Then came Stephen Burns, a name well known among skywatchers. On October 2nd, he uploaded a 9-minute time-lapse built from Perseverance's raw night sky images, and there, cutting straight across the Martian starscape, was a single white streak, thin, sharp, and perfectly linear. Burns had checked and rechecked everything, timestamps, star positions, frame alignments. His conclusion was cautious but chilling. The streak's speed, 60 km/s, was no camera glitch. It aligned exactly with the predicted path of 3I Atlas. For perspective, the Parker Solar Probe, the fastest human-made object in history, reaches 192 km/s only when it dives deep into the sun's gravity well. But here, far from any strong gravitational pull, 3I Atlas moved at 60 km/s effortlessly. At Mars's distance, such velocity belongs to interstellar wanderers, not comets born of our solar system. Burns didn't claim a discovery. Instead, he called for replication. "If this is real," he wrote, "then we're witnessing physics we've never seen before." His post exploded across astronomy forums. Thousands downloaded the same Perseverance frames, trying to reproduce his result. Some confirmed the streak. Others saw nothing. Heated debates followed. Was it a real celestial track, a cosmic ray artifact, a stacking illusion? But regardless of the outcome, one fact was undeniable. 3 Atlas had passed Mars, and the images, the one proof everyone wanted, were gone. For now, the only evidence was a faint line across a Martian sky, a whisper of something alien, gliding silently between worlds. In the days that followed, the astronomy community erupted into chaos. Stephen Burns's 9-minute time-lapse became a global phenomenon. Thousands of independent analysts, coders, and night sky enthusiasts rushed to download the Perseverance raw frames and run their own tests. For some, the results were undeniable. When they restacked the images, the streak appeared again, perfectly matching the coordinates of 3I Atlas. Even more astonishing, a few teams claimed to spot smaller, fainter trails, possible fragments following just behind it. Others saw nothing but noise. To them, the streak was a phantom, a byproduct of stacking errors, cosmic rays, or sensor noise. The online debates turned vicious. Every frame was dissected, every pixel questioned. What began as an exciting discovery quickly split the community in two, the believers and the skeptics. Then came a single frame that changed everything. At 0003 US, one team noticed a brief luminous green flash. It lasted no more than a few milliseconds, but it ignited a storm of speculation. Was this a real emission event? Something chemical, maybe even biological? Or was it just another artifact, a stray cosmic particle amplified by software? Experts pored over the color channels. The defenders of the real flash theory pointed to dicarbon, C2, a common molecule found in comets that glows green when exposed to sunlight. That, they argued, explained the hue perfectly. But others weren't convinced. They reminded everyone that Mars's thin atmosphere and Perseverance's sensors were both highly vulnerable to digital interference. A cosmic ray strike, they said, could easily create a single-frame anomaly. Still, the timing was too perfect to ignore. The flash appeared right when 3I Atlas was predicted to cross the field of view. If the event were genuine, it could mean the comet, or whatever 3I Atlas truly was releasing gas or energy in an unusual directional way, something no ordinary comet had ever done. But without the original unprocessed FITS files, no one could prove anything. NASA and ESA's silence became deafening. Normally, raw Mars orbiter data is posted publicly within days of downlink. This time, nothing. No quick-look images, no calibration files, not even a confirmation that the observations succeeded. The frustration reached boiling point. On forums and live streams, astrophysicists demanded answers. Was this simply a bureaucratic delay, or were agencies withholding data until they could explain what they'd found? Meanwhile, amateur coders began releasing their own stacking software, challenging others to reproduce the flash. The open-source spirit clashed with institutional secrecy. And all the while, one question echoed through every discussion. What if the flash was real? If so, it would mean that 3I Atlas wasn't behaving like any comet we've ever studied. It might not even be a comet at all. For a brief moment, in early October 2020, Mars became the best vantage point in the entire solar system to observe 3I Atlas. Earth's telescopes were blinded by the sun's glare, leaving only the orbiters circling the red planet to capture what could be history's most revealing close-up of an interstellar visitor. 3 spacecraft were given the task: NASA's Mars Reconnaissance Orbiter, MRO, equipped with the HiRISE camera, ESA's Trace Gas Orbiter, TGO, carrying KSSS, and Mars Express with its HRSC instrument. Each one was ordered to focus on a single moving target, a speck racing across the void 9 million kilometers away. The odds of success were razor thin. Even HiRISE, the most powerful camera ever sent to another world, could only hope to capture a few dozen pixels per frame at that distance. Worse, 3I Atlas was moving so fast that a single miscalculation in its trajectory would cause the entire target to miss the camera's field of view. Inside NASA's Jet Propulsion Laboratory, engineers rewrote imaging sequences overnight. The orbiters were commanded to point several degrees away from their usual positions, trying to anticipate where 3I Atlas would appear hours later. It was a high-stakes gamble. Aim too early, and the object would be gone. Too late, and it would vanish behind the star field. ESA's KSSS instrument was programmed to take a series of 4-color exposures, hoping to detect not just the comet's nucleus, but also any fragments or gas jets trailing behind it. Meanwhile, Mars Express's HRSC camera swept wide arcs across the predicted path, searching for anything unusual: clusters, outgassing, or asymmetrical plumes. Every observation required perfect coordination. Data from JPL's Horizon system updated daily, feeding new trajectory numbers to the mission teams. But there was no real-time tracking. Each exposure was blind, based purely on predictions. If even one data point was off, the cameras would photograph empty space. Still, the teams tried. They fought against bandwidth limits, cosmic ray interference, and the sheer difficulty of photographing a moving interstellar target from a stationary orbit. Then, silence. Days passed after the flyby, and the raw images never appeared. Normally, data from such high-profile events, especially those involving Mars orbiters, hit public archives within 48 hours. This time, the archive pages stayed blank. Inside NASA and ESA, internal messages leaked. Ongoing calibration. Signal anomalies under review. Verification in progress. But outside, the astronomy community wasn't buying it. For a world hungry for answers, the quiet felt deliberate. Was the delay about scientific integrity, or about what the images revealed? As one engineer later admitted anonymously, releasing the wrong frame, one with a single unexplained streak, could ignite a media frenzy overnight, but holding them back only feeds conspiracy. Caught between truth and caution, the mission teams hesitated. Every frame was a potential bombshell. Every streak, a possible misunderstanding, or a discovery that could rewrite what we know about interstellar objects. The silence stretched on, and somewhere beyond that silence, 3I Atlas kept moving, carrying its secrets deeper into the solar wind. When the first whispers of spectral data finally leaked from the Mars missions, the results didn't just raise eyebrows. They defied everything we thought we knew about comets. Comet science has simple, predictable rules. When sunlight hits a comet's nucleus, molecules like dicarbon, C2, break apart, releasing a bright green glow, so reliable that astronomers use it as a kind of fingerprint. But the readings from 3I Atlas refused to follow that rule. Early reports from ESA's Trace Gas Orbiter and Mars Express hinted at something chemically impossible. The green flash recorded in Perseverance's frames suggested dicarbon activity, yet the spectra showed almost no trace of it. Instead, the object's emissions were dominated by carbon dioxide and an unexpected surge of nickel lines, with almost no iron detected. For planetary chemists, that combination was shocking. No comet in our solar system behaves that way. Under normal conditions, iron outshines nickel by a wide margin in comet spectra. But here, the ratios were reversed. Nickel towering above iron by several factors. One researcher described it as like finding a frozen star's core trapped inside a comet. And that wasn't the only anomaly. The gases escaping from 3I/Atlas were rich in CO2, but almost completely lacking in water vapor, a direct contradiction to how comets evolve when heated near the sun. Water is supposed to lead the process. CO2 usually comes later once the ice sublimates. But 3I/Atlas was venting CO2 first, violently, while staying chemically dry. Then came the strangest feature of all, its jet geometry. Instead of trailing away from the sun like every normal comet tail, 3I/Atlas's plume appeared to shoot toward the sun, forming what astronomers called an anti-tail, a sharp, sunward jet of light and dust that broke every modeling convention. Computer simulations couldn't reproduce it. For a plume that steep and that bright, the object would have to be enormous and incredibly dense, resistant to being spun apart by its own outgassing. And yet trajectory analysis showed no measurable non-gravitational acceleration. Despite visible activity, 3I/Atlas followed its predicted path perfectly, as if its mass dwarfed any forces acting on it. The numbers implied something staggering, a mass of at least 10 billion tons, more asteroid than comet. The deeper scientists dug, the less sense it made. Its chemistry, its behavior, even its motion seemed to break the rules of natural comet physics. One by one, the easy explanations fell away. If 3I/Atlas was truly interstellar, then it wasn't just another traveler passing through our system. It was a contradiction, a riddle written in light and chemistry. And if those spectral readings were correct, then what passed by Mars wasn't a chunk of ice and rock, but something built differently. As 3I/Atlas faded into the glare of the sun, slipping behind its blinding light, Earth and Mars both lost sight of it. For 5 long weeks, no telescope could track its motion, brightness, or shape. The object entered what astronomers called a solar blackout, a period of enforced blindness when even the most powerful observatories must simply wait. But before the silence set in, one final calculation reignited the mystery. Dr. Arvid Lue and his team, known for their provocative research into interstellar trajectories, decided to trace the path of 3I/Atlas backward through space and time. Using JPL's Horizons database and Monte Carlo simulations, they compared the object's past coordinates to known astronomical anomalies. And what they found was unsettling. The projected path of 3I/Atlas passed through the same region of the sky where, in 1977, the famous WOW signal was detected, a mysterious 72-second narrowband radio transmission at 1,420 megahertz, the natural frequency of hydrogen. The odds of that overlap, according to their models, were only 0.6%. That number doesn't prove anything, but it's not nothing either. For SETI researchers, 1,420 megahertz is sacred territory, the cosmic calling card. If an intelligent civilization ever wanted to send a signal meant to be found, that's the frequency they'd choose. It's quiet, universal, and unmistakable. Nature doesn't broadcast in such a narrow channel. Lowe's team stopped short of declaring anything conclusive, but they argued that if any object ever deserved a targeted radio follow-up, it was this one. An interstellar body moving at impossible speeds, showing impossible chemistry, and passing directly through the coordinates of one of humanity's most enduring mysteries. Others called it coincidence, statistical cherry-picking, or wishful thinking. But even the skeptics couldn't ignore the poetry of it. A glowing green enigma from another star, sweeping through the same cosmic neighborhood where a strange voice once whispered from the void. By late October, 3I/Atlas disappeared completely behind the sun. And with it, so did our chance to observe it. For weeks, the world waited. Scientists, amateurs, and dreamers alike watched the calendar, counting the days until early December, when the object would emerge again in the pre-dawn sky. 4 questions dominated every discussion. Would its brightness change? Would its course deviate? Would its spectral fingerprints remain the same? And, most hauntingly, would it still be one object or many? Until then, only the evidence remains. Every anomaly, every debate, every missing frame adds to a growing dossier of contradictions. 3 Aamosh Atlas challenges comet science, planetary chemistry, and even our assumptions about what natural really means. It could be nothing more than a strange rock from another star, or it could be something that was meant to be seen. Either way, one truth is certain. An interstellar visitor passed through our solar system and left behind questions that no one can yet answer. And as it drifts back into the dark between the stars, so does the silence that follows it.